So this is the second part of working with base e. We're going to take a look at graphing e to the x and the natural log of x, and we'll look at solving a couple of equations with logs and exponentials. So the first thing that I have is my e to the x and natural log of the x charts all filled out because I didn't want to waste time punching buttons on the video. I know you guys know how to substitute and evaluate on your calculator. So all of these in the blue, of course, came from e to the negative 2 power, 0.135, and so on. And then for the reverse, remember the natural log is the inverse of e to the x. So I just took my values in the first chart and flipped them to get the values in my second chart. So to graph these, looking at my scale, I'm going to want something along the lines of, I think we'll just stick with the ones that we have. So negative 2 and about 0.135, so it'll be pretty close to the x-axis. Negative 1.3, 0, 1 of course, and 1 just shy of 2, or just shy of 3. And 2, almost 8, so that one doesn't fit on my graph. So here's our e to the x. So remember, all exponential growth functions where the base is greater than 1 will look something along these lines. And then all of the natural log functions, remember, inverses graphically are reflected across the line y equals x. So when I flip these points around, oops, that's negative 1, so we go here. Just plotting a few points here. It's a little harder doing it this way. And the other one's off the chart. So they look like this. All of the regular log functions will look like they grow slowly. And remember, the asymptote for the log functions is the y-axis, whereas the asymptote for the exponential functions is the x-axis. So now let's talk about domain and range for each of ours. And this, for e to the x and natural log of the x, it's the same domain and range as regular exponentials and regular log functions. So nothing changes with properties of logs because it's base e. So our domain for exponentials is all real numbers. We can raise a number to any power positive, negative, 0. The range, if you look at our blue graph, it stays entirely above the x-axis, which is the 0. Y equals 0 is our x-axis. So all of our y values are greater than 0. We never even get a value of 0 when we raise a number to a power. Over for the natural log, remember, it's flipped. So the range for the natural log is all real numbers. If you take a look, our graph has arrows going down and up on each end. And then the domain, because of our asymptote along the y-axis, is x is greater than 0. You cannot take the log of 0 and you cannot take the log of a negative. So the next ones, we're just looking at a couple of transformations of our e function and our natural log function. So again, I already had these evaluated, so we're not wasting time punching buttons. So the plus 3, remember, shifts it up 3. So think about where our original exponential function was, and now we're shifting it up 3. So we're going to look at what that does to the domain and range of our function. So I'm going to try and plot these points quickly. So looking at our new graph, the domain is still all real numbers. We didn't change what we can raise a power to. But the range, now if you notice, we have a new asymptote along this line, the y equals 3 axis. So our range is y is greater than 3. And when we look at 7.7, we're going to get into more detail with what transformations do to our asymptote, our domain, our range, and the x and y intercepts. And the next one is negative natural log of x. So think about, basically, we just multiplied all our y values by negative. So what will that do to the graph? Let's plot the points quickly. So think about the fact that our natural log, our original natural log function, looks something along these lines. So making it negative, flipped it over the x-axis. So our domain, again, didn't change. We still can't take the log of a negative, so our domain is x is greater than 0. And the range didn't change either. It's just facing a different direction. We're still growing towards the y-axis and then out towards infinity, so our range is still all real numbers. Last couple of slides, we're going to be solving some equations. So looking at A, we have the natural log of x plus 3 equals the natural log of 14. So when the logs have the same base, they cancel each other out essentially, and you can set what you're taking the log of equal to each other. So subtracting 3 from both sides, we get x equals 11. Over on B, I want to isolate the natural log first, so I'm going to divide both sides by 5. And then in order to cancel the natural log, I basically take e of both sides, so the e and the natural log cancel. So e to the third power is about 20.086. On C, I'll condense this to a single log first, before canceling the natural log. So subtraction of logs condenses it to division. And then I'll have e on both sides, or kind of using the curly log. So what I'll do here is I'll kind of set this up as a proportion and then cross multiply. So I get 12 equals x times e to the 4th power. So I'll divide both sides by e to the 4th. And x is about 0.220, rounded to 3 decimal places. And the last one, again, when I condense addition of logs, it condenses with multiplication, so 1 times x cubed is just x cubed. And then I cancel that with the e, so we have x cubed equals e to the 7th. And then I'll take the cube root of both sides. So we get x is about 10.312. Last slide, we're going to look at solving some exponentials. So for a, to cancel e, we're going to take the natural log of both sides. And x is about 3.219. On b, we've solved this before, and we usually use the common log. Just because we're working with base e now, I'm going to go ahead and use the natural log instead. You can use the log of any base as long as it's the same base that you're using. But our calculator only does base 10 and base e. So those are the two that we stick with when we're solving equations. So I'm going to use my power rule with logs, multiply by x. And then divide both sides by the natural log of 35. So we've got the natural log of 20 divided by the natural log of 35, and that's about 0.843. And if you try that with the common log, if you do log of 20 divided by log of 35, you'll get the exact same value. It's the change of base formula.